Thank you for tuning in today and welcome to Turbo Expo 2020. We're going to introduce multi-point design strategies for aero engines. This is joint work with the Swedish universities of Chalmers from Stockholm and Modelon from Westhaus. My name is Michael and I work for Modelon.
In the next 25 minutes, I will talk about the motivation for this work, the methodology with a well-defined table notation, and results in terms of workflow and simple case studies. In the end, I will summarize with conclusions. Multi-point design is a technique to capture the different requirements across a mission on an aero engine. This is illustrated in the slide. To the left, you see a simple commercial aircraft mission. The main plot shows altitude and flight levels with a solid line and the y-axis to the left. There's also a lot of other data, such as lift coefficient, Mach number, calibrated airspeed, fuel, etc. The main point is here that the cycle design must consider the whole envelope, and this usually works by covering different steady state performance points. Some of these points have to be covered or included, such as the ones marked with the dots here, but only one obviously can be the design point. In the classic cycle design, the design point is first evaluated and then several off-design simulations are run for other conditions. However, it can be quite tedious to iterate between design and several off-design simulations. Multi-point design is then this natural extension to sequential classic design, where we are solving a design problem and several off-design problems concurrently with the same numerical solver. This then also alleviates the need to manually track consistency between inputs and targets. They are simply formulated as residual equations or constraints. The objectives for this work were to extend the open literature on multi-point design. More specifically, we saw the need to introduce a proper notation. We also wanted to document to academic state-of-the-art multi-point schemes that might have been difficult to understand for engineering students before. Lastly, we wanted to compare the designs generated by these different multi-point schemes when we're using exactly the same cycle model for both of them. Here is our methodology. The table notation describes the equation set of the multi-point synthesis. The equation set really combines different parts, the design problems, several off-design problems, and then closure equations for sizing and operation. Now, much of this is really recasting existing single-point equations. So for instance, for the design problem and off-design problems, this has been already described elsewhere. See some of the references shown here. And the new part that we want to capture with this table notation are really these closure equations. This has often been described only in full text or covered partially. For instance, SCATUS DPMM, design point mapping matrix, and that's really the part that we're focusing on here. With this table notation, we're expanding work published before by Kyprianidis, see reference 15. And a key aspect here is the distinction between synthesis and target variables. The synthesis variables are usually chosen by the modelers as degree of freedom or computational input from all the variables that appear in the models. We can change these selections typically with flags when we compile the model. And then additionally, we're considering these target variables. They are in turn some degrees of freedom that the modeler wants to fix. Often they're really outputs of the computational model and usually can be selected by the modeler also after compilation. The tables then provide typical examples of synthesis and target variables. First, for operation in the middle, for instance, we can vary the fuel flow or fuel to air ratio until matching some net thrust or T4. For the sizing shown to the right, we can, for instance, use design OPER as synthesis variable and OPER in cruise as a target. We can use fan pressure ratio as synthesis variable and specific thrust as a target, and so on. So let's describe the table notation with an example, and this is simple turbojet. And you can see in the table to the left that we list the cases in the operating envelope as columns. This is similar to Scottish DPMM. And we take the design point as the first column. As rows, we first list the target variables. You can see that there are both the sizing and operating point categories. Then we list the synthesis variables, again in both categories, and the synthesis variables covering all columns because they cannot change from one case to another. And then within all the cells of the table, we describe the synthesis matching, and for that we use different keywords. For synthesis variables, we can use fixed. That means that the synthesis variable value is known and entered by the user. Also for synthesis variables, we can use the keyword variable. That means that the synthesis variable is not known, but modulated iteratively by the solver. Another keyword is target. That is used only for target variables, and it means that a target value is known and used as a threshold in a residual. You can also see that cells can be empty. That means that values can be computed from the governing equations, but there is not any value prescribed via any closure equation. Then if you look at the model diagram to the right, we can flip through the different aspects of this turbojet multi-point synthesis. For instance, we can see that we find the overall airflow and fuel to air ratio and the design point based on T4 and net thrust. We find OPER in design based on sum of design OPER target. And we compute all of design fuel to air ratio from off design FAR values. The table notation also allows us to classify design problems with respect to design and operation. The design, for instance, can be an explicit or implicit single point design. If you look at the left and the middle columns, in the left one, for instance, the sizing synthesis variables are fixed, and in the implicit one, the synthesis variables are modulated to meet targets defined only in the design point. In a true multi-point design, sizing synthesis variables are again free, and targets are imposed in at least one off-design case. The first academic state-of-the-art multi-point scheme discussed here originally came out of Granville University and was suggested by Professor Kyprianidis, now at MDH in Sweden. This has been used for several types of conventional and unconventional cycles. The main features are the use of an ideal velocity ratio, originally based on Guha, OPER with a pressure ratio exponent to define pressure ratios, and the specific thrust. To the right, we see the synthesis matching table and the suggested notation. Note that this was split into two parts due to screen space constraints. The second academic state-of-the-art multi-point scheme discussed here came out of NASA Glenn and was suggested by Jones and colleagues. This has also been used for several types of conventional and unconventional cycles. The main features here are the use of a non-ideal velocity ratio, OPER with a constant SPR and LPC pressure ratio to define the HPC pressure ratio, and T4 targets. To the right, we again see the synthesis matching table and the suggested notation. Should also note that the coded reference contains a variable area fan nozzle, which was discarded for the results generated here to yield an apples-to-apples comparison. Now we can talk about results in terms of the workflow and the trade studies. The results were created with the typical engineering workflow. The first step is to create a single point cycle model in a graphical environment where we're meaningful with the code editor. Then a couple of cases and confirm that the model behaves as expected. Also tag some of the results. These will be useful then later on when we're using more complex models because the single point results are usually easy to converge, and more complex multi-point schemes can require some work on initialization. So if we tag the single point results here, we can reuse them later on to initialize the first few simulations of the multi-point setup. In the third step, we semi-automatically create the multi-point model from the single point model. And then we again use a graphical environment to complete the multi-point setup. We then initialize the model the first time with the tagged single point results. And in the fourth step, we can leave the graphical environment and script some sophisticated analysis notebooks for parameter studies, numerical optimization, and so on. Lastly, we may want to expose some of the key trades to non-expert stakeholders via web apps with easy interfaces. The workflow and results were generated using Modelon Impact. This is a system design engineering software which is cloud native and accessible through the browser. The different steps of the workflow were implemented in the different views of the platform. We implement steps 1 through 3 in the model-centric view shown to the left. Then we switch over to notebook mode in the middle and run trade studies for step 4. Finally, we use the custom view shown to the right for step 5. We first open the graphical editor in the browser by typing in the address. We open a workspace and create a new model. In the model, we drag and drop components onto the canvas. We then connect the core and the bypass streams and the mechanical spool connections. We also connect the bleed circuits for customer bleed and cooling bleed and parameterize our components. After parameterizing the components, we extend the baseline plant model in the object-oriented sense to a simple single-point controlled experiment, configure the components such as the burner for external control. We summarize key cycle properties via the usual station naming scheme. After all thermodynamic stations were exposed to the summary component, we can run a design point. A name for the sizing data is defined, and the simulation results are named as top of climb design point. The results are viewed and checked for consistency. Then an off-design simulation is run by stepping the boundary conditions from a known solution to the ones of interest. Here, the Mach number, for instance, is changed at most by 0.1 increments. The results are named RTO for rolling takeoff. Second submodel is extended from the baseline plant model and configured again for external control, this time for both operation in orange and sizing in blue. When all external inputs have been routed to the outside of the submodel, another fully customizable function is run to generate the draft multi-point setup. We define names of design point and first of design model instances and the name of the multi-point model to be generated. The new model is then loaded, and we can see the two instances of the submodel called TOC for top of climb and CRZ for cruise. You can also see the code. Then we can use the drag and drop to complete the multi-point setup. Once we're ready to run the multi-point setup, we reuse the tagged single point results as guesses for the complex multi-point model. We define the name of the multi-point experiment and the mapping on reusing the results. Here we're reusing the top of climb results because we don't have cruise results to initialize the cruise point. The result is again named, in this case, OPER 50. With the first converged point of the multi-point setup, we're now ready for trade studies and can start writing analysis notebooks. Now in cycle design studies, we often vary several design parameters one at a time or concurrently, such as OPER or specific thrust. Here we say that we want to vary parametrically OPER, but first want to generate some results with some simplified multi-point schemes. This first one here is defined by taking the Cranfield scheme, but fixing bypass ratio and fan pressure ratio. Based on what we saw in the introduction on the state-of-the-art multi-point schemes, we can already predict this is likely too simplistic. The prescribed bypass ratio may yield a beneficial jet velocity ratio or not, based on the engineering intuition, chance, or iteration. This could be the case or could not be the case. The prescribed fan pressure ratio may be easier to guess or predict due to a simpler relation between FPR and specific thrust. The second simplistic scheme is also defined by starting from the Cranfield scheme as template, but this time only fixing FPR and changing the threshold for a specific thrust. That means that bypass ratio now has to be modulated to yield a given specific thrust. You can again deduce that this scheme is probably too simplistic, achieving the specific thrust target only through variation of bypass ratio can only work by increasing or reducing the relative influence of the core jet velocity, and as the jet velocities only vary mildly between the hot and the cold stream, say maybe 20%, the strategy is likely poor and also somewhat fragile. Additionally, varying the bypass ratio to achieve the specific thrust target influences the jet velocity ratio and probably moves it away from its optimal value. This slide then shows some of the results for the parameter study varying OPER. OPER is obviously the abscissa or x-axis of all these plots. And from left to right, the plots show as y-axis or ordinate the velocity ratio, specific thrust, and bypass ratio. We see that the dotted lines correspond to the case introduced first, the simplified scheme 1, where we fix bypass ratio and FPR, and the dashed lines only fix FPR and vary bypass ratio for the specific thrust target. For the velocity ratio, we can see that the fixed bypass ratio scheme with the dotted line leads to higher velocity in the bypass stream for higher OPER values, which is not desirable. Modulating bypass ratio to yield the specific thrust, that was the dashed line, results in better values, but these are also not optimal velocity ratios, as we can see from the inlet rule of thumb results shown in black and in the equations to the lower right. For the specific thrust, we see that both schemes result in comparable values, and we can also rate to the optimal values with the rule of thumb from Guha. Again, see the equations on the lower right. For the bypass ratio, finally, the fixed bypass ratio in design is shown versus the bypass ratio required to make the specific thrust target with the dashed line. Finally, in terms of the specific fuel consumption, we can see that the setup with fixed bypass ratio and fan pressure ratio yields better results. For this particular case, for all the cases with OPER higher than 45, and in terms of fuel consumption, therefore, the burst velocity ratio apparently has less impact than the specific thrust. Only when we reach OPER around 60, the inefficiency introduced by the mismatch in velocity ratio leads to nearly identical SFC in flight conditions. This also illustrates the importance of imposing a meaningful target jet velocity ratio. The paper has several additional trade studies and results. In this presentation, this is the last one that we're going to review and summarize. It covers the academic state-of-the-art multi-point schemes, and the dashed dotted line, the NASA-Glenn scheme, and the solid line, the Cranfield MDH scheme. Key takeaway on this slide here is a difference in how the two schemes set up the T4s. The NASA-Glenn scheme prescribes T4 in RTO, while the Cranfield MDH scheme prescribes T4 in cruise. And the Cranfield scheme then continues to derive the other T4s from the net thrust values, while the Glenn scheme defines the T4 in top of climb, the design point, from a temperature ratio that they call the thrust lapse requirement. Essentially, this defines how hard to run the core during climb in relation to the T4 in rolling takeoff. And then the remaining T4s are again computed from the prescribed net thrust values. The interesting result here is that despite the same net thrust in RTO, we get a substantial difference in T4 in RTO. And we can probably summarize the intuition behind these design schemes such that NASA's Glenn is trying to achieve approximately a constant temperature for the first uncooled component in rolling takeoff, while the Cranfield MDH scheme tries to achieve a consistent core cycle. Here are the results in terms of the previously discussed variables. We'll keep this short, see the paper for all the details. You can see velocity ratio specific, thrust and bypass ratio. We'll just highlight the bypass ratio here, where we see that for the NASA-Glenn scheme, very high bypass ratio values are again leveraged. This probably also factor in the high net thrust in RTO and low T4 in RTO results discussed in the previous slide. Lastly, we found that we get better SFC with the NASA-Glenn scheme, in particular at high OPER. The value we're most interested in here is the orange one for the nominal cruise condition. And in addition to the aspects discussed in the previous two slides, there are two more properties of the analysis that are important here. You can see them to the right on the slide. First, with the high OPER, the HPC last stage blade length reduces, and eventually the tip clearance deteriorates the polytropic efficiency of the HPC. And additionally, and this is shown in the plot to the lower right, due to the different T4s, there are large differences in the cooling flows for the HPT. This already takes us to the conclusions. We saw the improved notation for those multi-point schemes and the documentation of the two state-of-the-art schemes. We saw results for different schemes and the same cycle model We also discussed how the designs differed between the Glenn scheme and the Cranfield scheme in terms of the design rationale. We also put the targets in context based on analytic rules of thumb by Guha. And in the paper, you can learn about several additional differences. In case you have any further comments or questions, please reach out to me or my colleague Thomas. We thank you for your attention and hope that the work presented was interesting to you.